Okay, hi, good morning, and welcome everyone. I am very pleased to welcome today Professor Babak Hassibi from Caltech. He is a full professor at Caltech currently and the executive officer, which is the same as the chairperson of the EE department at Caltech. He got his PhD at Stanford, and he was a member of technical staff at Bell Labs for several years. Babak has worked in many diverse areas. He has actually made contributions to areas from communications, especially multi-antenna systems back in Bell Labs, and the information theory and the coding theory behind the various communication systems, especially MIMO, as well as in other areas like control, robust estimation, signal processing in general. So very diverse, covers a big range of areas. And many awards as well have been given for his work, including, for example, a Packard Fellowship and a PK's Presidential Early Career Award. Today, he will talk to us about phase retrieval for sparse signals. Thanks.
Thank you very much, Mariam, for the kind introduction. It's a pleasure to be here. I got to see familiar faces this morning, so I saw a batch of Caltech students who are now graduate students here. I think I was last here 3 years ago, gave another seminar, not in this department, but it's a pleasure to be back. Before I start, I should maybe, I don't want to say it as a word of wisdom, but, do not procrastinate would be my message today, because that's what I did this weekend. And I have a proposal due at 3 p.m. today, and I was up all night last night trying to finish it for that reason. And so I hope I am, awake enough to be able to give this talk. So I apologize for that if I mumble a little bit. So please do not procrastinate, I guess is the message. Okay, so what I want to talk about today is phase retrieval for sparse signals. Now, phase retrieval is a very classical problem in signal processing. It goes back to the early days of, when people were measuring spectra of things and looking at Fourier transforms. So as you all know, when Fourier developed the Fourier transform, it really opened a whole new vista in terms of looking at signals. People, I would say, a few decades after that, maybe 50, 60 years when Fourier optics was being developed, were actually able to, measure the Fourier transforms of various signals. And one of the early things that they encountered was that, measuring the phase of the Fourier transform of a signal is a lot more tricky than measuring the amplitude. The amplitude is often just the intensity. It's much easier to measure. The phase is different. And so in many applications, people quickly realized that, it would be nice if one could recover the signal, with partial phase information or, not having to measure the phase. And so it's been a classical problem since then. It's called phase retrieval. And so so it has a history of more than 100 years. And, so one would think that after 100 years, there's probably not a whole lot more to say. And so what I want to talk about today is some recent work we've done. Again, this is a classical problem. But in signal processing, there's been an emergent area some of you might have heard of called compressed sensing. And so what we've done here really is revisit this classical problem from the viewpoint of compressed sensing. I'll talk more about that as we get into the talk. So it's an old topic, but the tools are new, and so hopefully we'll get some new insight to the problem. And this is joint work with two of my graduate students, Kishore and Samet, and Kishore really is the prime author on this. Okay, so here's the outline of the talk. I'll start off with a little bit of an introduction, kind of introducing the problem, motivating where it comes from. And then I'll focus on the sparse phase retrieval problem. And so what that means is that we will be looking at signals who, in the time domain, are sparse. As we'll see in a moment, and I'll make clear, if you want to recover a signal from the Fourier transform, you need the entire Fourier transform. You need the magnitude and the phase, and then you do the inverse Fourier transform. You get the signal. And so if phase information is not available, you need some other a priori knowledge or some other constraints to allow you to recover the signal. And so the structure that we will be looking at is that the signal is sparse in the time domain. And I'll try to argue that this is a relatively common feature of signals that one encounters. So I'll talk a little bit about that. I'll talk about whether sparsity will allow us to identify the signal uniquely or not. I'll relate the problem to something called the turnpike problem, which also comes up in bioinformatics. And so we'll see that. I'll describe the algorithm that we have for signal recovery, and then I'll conclude. So that's the outline. So as I said at the beginning, actual physical systems that measure, say, the spectrum, in some cases, all the output is just the squared modulus of the Fourier transform. So they can measure intensity. As I said, it's a lot easier to measure intensity than it is to measure phase. Okay? And so once phase information is lost, signal recovery becomes challenging. In principle, if you know nothing else about the signal other than just the squared modulus, you cannot recover it, right? Because you need the phase information to do the inverse Fourier transform. Okay? And so often one has to have some other type of structure, and we'll talk about that. But as I mentioned, this is a fundamental problem. It arises in many areas of engineering and applied physics. And I've listed a few here: optics, X-ray crystallography. So you want to figure out, the atomic composition of some material, some crystal. It comes up in astronomical imaging. It comes up in wireless communications if you're doing what's called non-coherent or blind deconvolution, right? So you don't know the input, you don't know the phases. You want to figure out, say, the channel in the signal. And so, the problem, so we'll be looking at, as I said, it's the recovery of the signal from the magnitude of the Fourier transform. So that's what it really is. But we will kind of be looking at the problem mostly through its time domain counterpart. And so what is the time domain counterpart of the Fourier transform magnitude? Does anyone know? It's the autocorrelation function, right? So if you take the magnitude square of the Fourier transform of a signal and take its inverse Fourier transform, it's the autocorrelation. Okay? So knowledge of the autocorrelation is equivalent to knowledge of the magnitude of the Fourier transform. Okay? And so we'll often find it more convenient to work with the autocorrelation, as we'll see in a moment. But in either case, whether you're recovering the signal from the autocorrelation or from the Fourier transform magnitude, the problem is known as phase retrieval. Okay? So let me kind of set up the problem briefly. So we have a signal represented by x, and so it's a discrete time signal of length n, so x naught through xn minus 1. As I said, rather than look at the square of the magnitude of the Fourier transform, we can look at the autocorrelation function. The autocorrelation function, it's a sequence of the same length. Autocorrelation function is two-sided. It has symmetry, and so we only look at the positive side of it. And the way it's defined is through a convolution. It's the convolution of the signal, which is unknown, and its mirror image, which is what x tilde is, or the time-reversed version of it. So you take a signal, you convolve it with its time-reversed, you get the autocorrelation function. Okay? So that's what we can measure. Okay? So the phase retrieval problem is very easy to state. We want to find the signal x subject to the autocorrelation equations. And of course, the reason why this is difficult is because, the equations there are nonlinear, they're quadratic and are unknowns. In particular, there's something that's called non-convex, which essentially means there's lots of bumps and it makes the problem difficult. Okay? So if you think about it, as I said, in general, if I give you the magnitude of the Fourier transform, unique recovery of the signal is not possible because you need the phase. And so in all applications, the only hope that one has is that there's some additional a priori information that one has that will facilitate recovery of the signal. Okay? And so people have looked at different types of a priori information. There might be constraints on the location of certain non-zero entries. If you're doing X-ray crystallography, you might know some of the atoms that are composing your material. In communications, you might know constraints on the signal values. You might know that they're coming from some constellation. So there's a priori knowledge that you might have, and you attempt to exploit that. Okay? Nonetheless, if you take into consider all of these, there are some trivial ambiguities that we have to live with anyway. And so let me see if you guys can kind of figure out what they are. So the first is that if I have a signal and I do a global sign change, so if I change the signal from x to minus x, the magnitude of the Fourier transform or the autocorrelation function won't change because it's all quadratic. Are there any other ambiguities that can come up? Time shift, thank you, that's the next one. Because if you take a signal and you time shift it, what happens to the Fourier transform? It introduces a phase. And so if I do the square modulus, that phase evaporates, right? Because it has magnitude 1. There's one more. Come on, you guys have taken signals and systems. It's time reversal, right? If I take it and I take the mirror image, it's the same thing. So actually what happens is that these three operations render, if you will, the absolute value of the Fourier transform or the autocorrelation function invariant, okay? So, So these trivial ambiguities are there, and there's not a whole lot that you can do with it. And so in signal recovery, if we can recover the signal up to either a global sign change or a linear time shift or a time reversal, we're happy. We'll consider the problem solved because this is something we can't really deal with. Okay? So I don't want to say a whole lot about existing algorithms, but as I said, this problem has been around for more than a century. And so there are a whole bunch of algorithms that attempt to use this a priori knowledge to figure out what the signal is. And if you look at them, most of them fall into a class of algorithms called alternating projection algorithms, meaning that you're looking for a solution, and it lives on the intersection of a convex set and a non-convex set. And you kind of alternate between the two. And you might converge to a point that's a local minima, or maybe you'll get the solution. Anyway, so it's a very heuristic method. And just to give you a sense, a very good review paper of what was going on is a 1982 paper. Now, for me, 1982 is not very far away, but for some of you, maybe that is a ways away. And so if you have something where the review paper is back in 82, it tells you something about the field. Okay. So what do I want to talk about today? So today, the focus is on a particular type of structure called sparsity. Okay? And as I said, this is a structure that has gained a lot of traction in signal processing, in statistics, in machine learning. In many cases where you have high-dimensional data, people kind of believe or like to believe that even though it's high-dimensional data, it lives in some low-dimensional space. And so one manifestation of that is you have a signal, a time signal, but maybe it's sparse. It's only non-zero in a few locations. And again, there are many applications of this. If you think of astronomy, if you're doing astronomical imaging, you're interested in the location of stars, and you don't have stars everywhere. It's kind of sparse. Again, if you're looking at crystallography, same thing. Things are not all that dense. If you're doing seismography, you're looking for oil, or you want to figure out what the layers under the ground are, so you typically, maybe do sonar, and you look at the reflected signal, and the phase is difficult to measure, but again, you have very few distinct layers. You'll get a few reflections. In wireless communications, again, if you're looking at some channel model, and if you're in an environment where there are few dominant multipaths, again, the channel is sparse. Okay? So this is not to say that sparsity shows up everywhere. It doesn't. But there are a lot of applications where it does. Okay, and so what we'll focus on in this talk is what we can do if the signal is sparse. Okay? So I'm going to introduce a little bit of notation. So I'm going to denote by the set V the support of the signal. So V is the set of time indices I where the signal is non-zero. Easy enough. That's called the support of the signal. Okay? And so sparsity basically means that the size of this support, so the number of time instances where the signal is non-zero, which I'll denote by K, is a lot less than the duration of the signal, which is N. Okay? So there are far fewer stars than, the whole sky, if you will. Okay? And in particular, as we'll see later on, the regime I will be interested in is when K is kind of like the square root of N. Okay? So if you're thinking of N being, 1,000, then K is on the order of 30. That's kind of the setting. Okay, so now we can set up the sparse phase retrieval problem, which is, again, we want to find this signal. It's subject to the autocorrelation constraints, which I've written here. But we have an additional constraint saying that the support set is a lot less than N. Okay? So we have this additional constraint here. And so the hope is that this will help us resolve the phase. However, it might help us resolve the phase, but it still will not resolve the trivial ambiguities. Because if you have a sparse signal, if I change its sign, it's sparse. If I shift it, it's sparse. If I time reflect it, it's sparse. So the trivial ambiguities will still remain with us. Okay? And so the first question is, does sparsity in fact guarantee uniqueness up to trivial ambiguity? In other words, if I give you the autocorrelation function, or if I give you the magnitude of the Fourier transform of some signal, and all I tell you is that this is coming from a signal that's sparse, is that enough to resolve the phase? So that's the question. And our first result rather surprisingly says that that's the case. It's almost always the case. There's an exception to it, and so I'll read the theorem and then I'll explain what it means. So signals can be uniquely recovered up to, again, these linear shifts and time reversals from the autocorrelation or from the magnitude of the Fourier transform, almost surely, meaning with very high probability, probability 1, as long as the support is non-periodic. So periodic support, would be one where, for example, you'd have a period 2 support if you were non-zero at time 0, time 2, time 4, time 6. That would be a periodic support. Or if the period were 3, it would be 0, 3, 6, 9, so on. So as long as the signal is sparse but has a non-periodic support, just the fact that it's sparse fixes the phases. Okay, so this is good news, because it says in principle, even if I only have a few non-zero, or rather a few zero entries in my signal, they are sufficient for me to reconstruct the signal. I can reconstruct the phases in principle. There's this uniqueness result. Okay, so it's kind of like an identifiability result. It says as long as I have a few non-zeros, that's enough. The question, of course, is how to recover the signal. And so, I want to introduce, a technique that is used for these types of problems. Some of you might have seen it, some of you might have not, but I want to do it because it's an interesting technique and it's one that people use more and more these days. And basically it says whenever you see quadratic constraints, which is what we have here, try to lift it to something linear, and you'll see how this is done. Okay? So recall X was our signal, and I'm representing it as a column vector. Okay? It's an n-dimensional column vector. It's our signal. It's a vector whose entries are time instances. And then I look at this capital or bold X matrix, if you will, which is the outer product of X and X transpose. So it's a rank 1 matrix. It's a column outer product with a row. Okay? So I can rewrite this phase recovery problem in terms of capital X. Okay? So again, rather than little x, I want to find capital X. I have my sparsity constraint. Previously, it was saying that, little x has a support that's a lot less than n. To capital X, which has n squared entries because it's a matrix, what this means is that the points where it's non-zero is a lot less than n squared. This guy will have support k squared. Okay? And then these equations here are just a rewriting of the autocorrelation equations. I've written it as some linear operation on x, because if you think about it, capital X contains all the quadratic terms that you can get from little x. That's what an outer product does for you. And so in terms of capital X, this is a linear equation, whereas previously it was quadratic. We still have the sparsity constraints, but now we have a rank constraint too. We have to guarantee that the rank of this x is 1 because it's the outer product of two vectors. Okay? So even though my constraints here are linear, the rank constraint is guaranteeing the two problems are equivalent. Okay? And you can spell out what the A's are. I won't do that. There's no need to do that. Okay? So we haven't, the problem is still non-convex because we have this rank constraint, right? And it's non-convex because, what does convexity mean? If you have 2 points and if they're in a convex set, their convex combination should be in the set, but clearly convex combinations of rank 1 matrices will typically be rank 2. So it's not a convex. Okay? So lifting, the next thing you do is convex relaxation, and convex relaxation is basically done by dropping the rank constraint. Just ignore it. Okay? And then we have a sparsity constraint. We want the support to be small. And compressed sensing tells us that, if you're interested in sparsity, a good surrogate for that is to minimize the L1 norm of the signal, which is the sum of the absolute values of the entries of the signal. Okay? And so the problem essentially relaxes to the following thing. So we got rid of the rank constraint. We replaced it with a non-negative constraint because capital X is non-negative. We have the autocorrelation constraints that are linear, and then we minimize to promote sparsity the L1 norm of X, the sum of the absolute values. Okay? So this is what people typically do. And usually if you take a quadratic problem and kind of turn it to something convex like this, this is a convex program. This is readily solved because this is a linear constraint. This is a convex set now. Sum of non-negative matrices or convex combinations of them remain non-negative. And this is a convex constraint. Okay, so this is a problem that you can solve. You can, maybe 5 lines in MATLAB is what you need to write down the code that will solve this. Okay, and so typically this thing works well, okay, on most problems. But here, so the way you actually look at this, you solve this problem, and if you get a rank 1 solution, then you've solved it. You get the optimal one. If it's not rank 1, then you're in trouble. And so, as I said, this typically works, but in this case, it's the first thing you'd think of doing. And so when we look at this problem, after 15 minutes, this is what you think you should do. It takes you 5 minutes to program, and then you run it, and it takes you 5 minutes to realize it doesn't work. And not only does it not work, it fails miserably. So doesn't work is an understatement. Can anyone see why this can't work? So the reason is the following. It has to do with these trivial ambiguities, okay? So if I have a sparse solution, okay, say one of the sparse solutions, if I take that sparse solution and I say I do a time shift, excuse me, if I do a time shift, that's another possible solution, and it will lead to another rank 1 matrix, and it'll also satisfy the autocorrelation constraints. And in fact, it'll have the same L1 norm, right? Because if I just shift the entries, I'm still summing the absolute values of all the entries, so that doesn't do anything. So any 2 of these trivially ambiguous solutions, if you will, satisfy the constraints, and they have the same cost. And so any convex combination of them will have a lower cost. Okay, so the minimum of this will never be rank 1. It'll always have rank higher than 1 because it'll be in the convex hall, if you will, of all these different rank 1 solutions that you get from these shifts and reflections. Okay, so this fails. And as I said, typically this relaxation works. Here it fails, and the reason why, as I said, it fails is because the non-convex problem that we're trying to solve has multiple global minima. And so no convex relaxation can really capture it. Okay? So that didn't seem to work. And again, the problem is that we have this symmetry that you can shift and you can reflect, and that really hurts you. Okay? But, what I always tell my students is, when you can't solve a problem or you're stuck, change the problem. And so that's what I'm going to do. Okay, so I can't solve this problem, so I'm going to solve another. I'm going to show you a problem that I can solve. And then we'll come back and we'll learn something and we'll go back to our problem. So suppose somehow I knew this support of the signal V. Okay, so someone comes from heaven, whatever, and tells you, yeah, this is the support of the signal. So suppose I know it somehow. Okay? So if I know the support of the signal, then the problem becomes a little bit more specific. So again, I want to find this capital X matrix that's rank 1 that satisfies the autocorrelation constraints. But if I know the support, I know the positions where it's non-zero. Or in other words, I know the positions where it's 0. So these constraints become a lot of equality constraints, because once you're outside the support, Xij is 0. But in some sense, if I know the support, this breaks the symmetry, right? Because if I know the signal is 0 in certain areas, then the shifts may not have that property, or the time reflections may not have that property. So it breaks the symmetry. And so now if you do the relaxation, which again is to replace, say, X either with the L1 norm or the trace, it doesn't really matter here. These are the autocorrelation constraints. This is the support constraint, and the rank 1 is relaxed to this. Okay, so let's assume we do this. The trace, again, so Mariam is the expert on this, is to as a surrogate for the rank. Okay, so you can do this. Again, this is a convex program. Again, it's maybe now 6 lines in MATLAB. And let me show you the results here. And so this works. So what I have here is, so I'm looking at 2 problems. I don't know if these are, whether you can read these. So I'm looking at n equal to 64 and n equal to 128. And what I have here is I'm running over different values of the sparsity. That's what the x-axis is. And the y-axis represents my, probability of success. So I instantiate, many, many instances of this problem. So I randomly choose a support, I construct a signal, I solve the convex program I just showed you, assuming I know the support set. And what it looks like is we can recover the signal up to sparsity that's roughly n over 2. So the blue curve is for n equal to 64, and it looks like around, between, close to 40 is where this bends off. So, it looks like it's around n over 2. The green one, same thing. It looks around, it's between 60 and 70. So it looks like there's a theorem there to prove saying that if you know the support, the program I showed you recovers the signal if the sparsity is up to half the signal length. Okay? So this is good news, but again, this relies on the fact that there's some deity who comes down and tells you where the signal support is. As I said, this is a different problem, but this one was easy. Okay, and so that's what you usually do, right? You can't solve the original problem, you change the problem, you can solve it, and now you go back and say, well, can I use this fact to help me to solve the original problem? Okay, so if I know the support of the signal, things become a lot easier. And so the question now becomes, how can I recover the support? So let me forget about recovering the signal. Let me focus on trying to recover just the support, because I know if I can get the support, there's hope in getting the signal. Okay? So the way we're going to do this is, to simplify things, is I'm not going to find the support of the signal from the entire autocorrelation function. I'm going to attempt to find the support of the signal from the support of the autocorrelation function. Okay? So recall V was the support of the signal. W will denote the support of the autocorrelation. Okay, so the autocorrelation is another sequence. It's obtained from convolving the signal with its mirror image. And so its support are the time indices where it is non-zero. Okay, so that's some set W. And my goal is to find W from V, and there's a simple relationship between W and V, which is the following thing. So if you think about what convolution does, if you take a signal and convolve it with its mirror image, where will the autocorrelation function be non-zero? You know, if you think about it a little bit, you know, because you're convolving something with the mirror image. So basically, W will be the set of time indices that are represented by I minus j, where I and j come from the support of V. So for any two time instances in X that are of distance I minus j, if you convolve, that number will show up in the support of the autocorrelation. Okay, because what are you doing? When you autocorrelate, you reflect one, that gives you the minus j, and then you multiply them. And so when they meet is when you get a non-zero entry. Okay? And so what this is saying, really, is that the support of the autocorrelation function is nothing but the set of the pairwise distances of the support of the signal. Okay, so you have the support of the signal. You look at all the pairwise distances. That gives you the support of the autocorrelation. Okay, so the problem that we want of trying to recover the support of the signal reduces to the problem of recovering a set of integers V from the set of their pairwise distances. Because that's the problem. Okay? So it turns out this is it's a well-known enough problem that it has a name. It's called the turnpike problem. Now, I don't really know what turnpike means. You know, as Mariam suggested, you know, I spent a couple of years in Bell Labs, and there was a New Jersey turnpike there, and so I assume this is a Bell Labs thing. I mean, I don't know where it came from. It's called the turnpike problem. Okay? So the problem is basically stated as there's a set of n integers that are unknown, and we want to recover them from the multiset containing their n choose 2 pairwise distances. So the question is, if I give you these n choose 2 pairwise distances, can you recover for me the n integers? That's the turnpike problem. Okay? So for example, this could be my set that I don't know. It's my unknown set, 2, 5, 13, 31, 44. This is the set of the pairwise distances. Okay? And so the problem is I give you this, you give me that. Right? That's what we want to do. Okay? And again, if you think of it, there's also the same trivial ambiguity for this problem too. You can take the set V, you can add any number to it. That corresponds to shifting. And you can add and subtract it, which corresponds to, you know, reflecting it. Because when you do these things, the pairwise distances don't change. Okay? So again, if we find any solution subject to these ambiguities, again, we're happy. Okay? And so the aim is to recover this set up to translations and flippings. Okay? Now this problem is an interesting problem, I guess, in computer science parlance, because no one knows whether it's NP-hard or solvable by polynomial time algorithms. So people don't know where to place it. So maybe that should scare us a little bit. It's not clear we've made the problem any easier. But what's interesting about this and why people care about it is it comes up in other applications. And so I'm going to digress for a moment and say something about a computational biology problem where this turnpike problem shows up. Okay? It comes up in DNA site analysis. Okay? So the problem basically is this. So, you know, the human DNA is, I don't know how many hundreds of thousand base pairs long. It's a very long thing. And so you might be interested in, you know, a particular subsequence, say GAA-TTC, and for whatever reason you want to know where this occurs in the genome, right? It might be the biomarker of some disease or whatever, and so you want to know where it is, okay? And you don't want to sit and sequence the whole genome. That'll take too long. You just want to find where this thing occurs, okay? So among the miracles of biotechnology, you know, for any such sequence, it turns out that you can actually design enzymes that recognize this sequence, and when they encounter it, cut DNA right there. Okay, so you can do these kinds of things. And so what happens is, so assume this is your genome here, or the whole sequence, and these are the sites where this sequence is occurring. And so you'll have a solution with, I don't know, gazillions of these strands of DNA, and you pour in the enzyme, and the enzymes move around randomly. It's Brownian motion. And whenever they encounter this site, they will cut things. And because everything is random, you don't know where they're going to cut. So, this particular one strand might be cut here. Another strand might be cut there. Another one could be cut here, right? And, you may not have enough enzymes to cut everything everywhere. So you'll get these random cuts like this. And so once you get this, you can kind of do mass spectroscopy and measure the lengths of these cut sequences. And if you think about it, the length of these cut sequences are just the pairwise differences of where the sites are, right? So this one here is this pairwise distance. That one there is that pairwise distance. And so you end up with a turnpike problem. You end up measuring all the pairwise distances of the sites where this particular sequence is, and you want to go back and recover and see where the sequence was actually sitting. Okay? So this is the origin of the turnpike problem. But as you see, it comes up very naturally in this autocorrelation problem that we've been looking at as well. Okay? So there do exist algorithms that solve the turnpike problem, and one is called backtracking. So I'll explain it to you because it's easy to explain, but also because it's the way not to solve this problem. So let's go through it. So let's assume we've been given, so this is the example I showed you earlier. This is the support of the autocorrelation, or it's the set of pairwise distances, and we want to recover V, okay? So if I look at this thing here, okay, now one thing is clear, so one end is 0. We'll just put it at 0. This 42, which is the largest one, signifies that I have to have another integer 42 away. That's for sure. Right? So I know the extent of the signal is 42. Okay? So that's clear. What can I say next? Is there anything else I can say? There's one thing I can say. So this guy 39, where can it go? You see, the point is, so all these other numbers here, they're pairwise distance. So 8 here, right? The number 8 is the distance between some 2 points somewhere here, right? I don't know what 2 points. But 39 is special. Because it's the second largest distance, it has to correspond to some point that's either 39 units away from 0 or 39 units away from 42. There's only 2 possibilities for where that guy goes, okay? And so the rule is, there's 2 possibilities. Always take the one to the right, okay? So 39 is the next point, and should we take it from the left or the right? The rule is always, unless proven otherwise, take it from the right. So I'm going to put a point here, okay? And so now I have 3 points. So I have a distance 39. I also have my distance 3 because, that distance is there too. Okay, so then I end up with a smaller support. And now what do we do? Well, the next point is 31, right? And so 31 has to either be 31 from 0 or 31 from 42. There's only 2 positions it can sit. And again, you put it on the right. Okay? And so now you look at the remaining pairwise distances after you compute all of these guys. You have this. So the next guy is 29. And again, 29 has 2 places it can go. It can either be 29 from 0 or 29 from 42. We always take it to the right. And so 29 from 42 is over here. It's 13. Is this permissible? It's not, right? Because if it were, I should have a distance of 2, and I don't see 2 here. Okay? So it has to be on the other side. It has to be 29 from 0, so it has to be somewhere here. And in fact, when you put it there, you end up with all the pairwise distances, and the remainder is empty. And so we got back this set, 0, 3, 11, 29, 42. The original set was this, and they're off by 2. So we did recover. Okay? So this is an algorithm that you can explain. It's simple. But you never ever want to do this, right? Because this is a binary search, right? At each time you have 2 choices, and on average, half the time you're going to guess wrong. And so you're going to have to exponentially search, So it's good if you have like 6, 7 points. Beyond that, I wouldn't recommend that you do this. Okay, so it's the worst case complexity. In fact, the average complexity is exponential. Okay. The other problem is this: it doesn't work in the circular case because this really relied on the fact that you had ends. If you're doing circular convolutions, which in some applications you have to do, then all bets are off, right? There is no beginning and end, and you can't even tell anything from the second largest. Okay. How much time do I have, Mario? 10 minutes. Okay. Okay. So that's that. And so what I want to describe now, if I can do it quickly, is the algorithm that we have. And I can't get into proofs. They're technical, but I'll just describe the algorithm. And then I'll show you some simulations. And I'll end with some comments. Okay. So what we've developed is an efficient algorithm that in a certain, as you'll see, under certain restrictions actually solves the problem extremely efficiently. Okay? So here's what we're going to do. So recall V was the set that we're looking for, and W is the set of the pairwise distances. So this has cardinality little k, that has cardinality capital K. Okay? And we're looking for any set U that is either a reflected or shifted version of V. Okay? And so to resolve the trivial ambiguities, I'll always assume that U0 is 0. So I'm going to fix the one endpoint at 0. And then I'm going to fix the orientation by insisting that U1 minus U0 is less than UK minus 1 minus UK minus 2. So that kind of fixes it. Okay, and then I'm going to define one other thing. I apologize. So in the next 5 minutes, I'll have a little bit of math here. Uij is the absolute value of uj minus ui. So it's the pairwise distance between I and j. And I'm going to define a set, not define, but with this definition, the set U is nothing but the set U0j, because it's the distance is from 0. If you take one point to 0, the distances from 0 are just the points we're looking for. Okay? And W, of course, is Uij, because it's the pairwise distances. And so it's clear that U is a subset of W, right? Because 0 is one of the i's. Okay? So if you stagger something to the origin, then the support of your signal, which is unknown, is a subset of the support of the autocorrelation, which is known. Okay? So the name of the game is I want to find, if you will, smaller and smaller supersets of U. We'll see that in a moment. So let's assume, again, this is how you solve problems. When you can't solve a problem, just assume something, and then see if you can make that assumption happen. So assume I know U0p for some p bigger than 1. So I happen to know one of the points in my support, the pth one. Let's assume I know that. If I know that, then I can define a set UP, which is just the set of points including an after p. So it's the U0j's for j larger than or equal to p. And I can define another set, which I'll call W of p, which is just the original set W, where I'm adding to it this one point that I know. So this means I'm adding to every point in W, U0p. Okay? And the claim is that this UP, this guy here, is a subset of W intersected with WP. These things I can compute. Okay? And this UP, of course, is a subset of U because it's part of the U I'm looking for. But these two, if I know U0p, I can compute. And the reason why this is true is, well, certainly U0j, right, which is the elements of UP are U0j's. They're in W because U is a subset of W. But they're also in WP because UPJ is in W. And therefore, U0P plus UPJ, which is nothing but U0J, that's how pairwise distances add up, has to be in WP because that's the definition of WP. It's stuff in W plus U0P. So U0J is in both, therefore it's in the intersection. Okay, so that's the argument for that. Okay? And so you can extend this idea to multiple intersections. So if I have a whole bunch of these, suppose I give you the first T entries in the support, then I can similarly define a collection of WPs, which is just W plus the corresponding U0P. And then it turns out that this set, or the set UT, which is all the U's after T, is actually a subset of the intersection of T things. And so the reason why we're doing these things is because, as I said, we want to get tighter and tighter supersets on U. And so this has T intersections. It looks pretty tight. Okay? So we can do this kind of stuff. The only question that remains is how can I actually, get these, whoops. I'm sorry. I'm trying to not use the laser pointer. But anyway, the question is how to find, say, the first two entries, the first T entries in the support from W. And that comes from a graph step. And I'm worried that if I go through this, I'll lose you guys. How much time do I have, Marianne? 5 to 10 minutes. Okay, then maybe I will. Okay. Because after this, I don't have a whole lot. So here's the graph step. So this is a combinatorial algorithm, right? So suppose I give you an integer set, z0 to, say, z size of z minus 1. So it's a bunch of integers. And here's how I'm going to construct a graph gz out of them. So this graph, any graph, has to be defined through a set of vertices and a set of edges. So this graph, as its vertices, will have the integer z in this set. So each element of the set will be a vertex in this graph. And I will draw an edge between two of these vertices if the pairwise distance between those two vertices is unique. In other words, if there's no other pair that gives me the same pairwise distance. So that I can construct a graph this way. So for example, if my z is this is the graph that you get. So for example, 2, 5 is an edge because 2 minus 5 is 3, and there are no two other entries here that have distance 3, I hope, I guess. And so 5 and 19 are not connected because 5 minus 19 is 14, and 14 is also obtained by 67 minus 53. Okay, so you get a graph like this. Now, what is this useful for? Well, you can use it to construct some elements from the support. And the idea is this, okay? So if I have some set Z, which is a superset of U, but a subset of W, so it lives in between, okay? Then, if I construct its graph, the claim is that if there is an edge in this graph between integers zi and zj, then both zi and zj have to be in the support. Okay, so that's the claim. And the reason, again, if you think about it, is easy. So if zi minus zj is an edge, first of all, it has to be in W because I guess that was the definition of gz that I should have mentioned. Now, why is it in W? I guess it's in W because z is a superset of U. And that's the pairwise distances. The reason why they're both in U is because if there's an edge, it's the unique zi and zj that give me this pairwise distance. And if it's the unique one that gives me the pairwise distance, that has to be in U too, because U also gave that pairwise distance. Okay? So that's a fact. So any edge that exists in GZ is actually in the support. Okay? So with that introduction, I can quickly describe the algorithm. Okay? So you start off with W. Okay? you have the support of the autocorrelation. U01 is easy to find, as we said, because we know the two edges. U01 is found from the second largest distance. Okay, so U01 is known. And so I can compute W1, which is you take the set W and you add to every element U01. Okay? And then what I do is now this, if you recall, from an earlier statement that we had way back when, here, W intersection WP, or in particular W1 here, is a superset of U. Okay, so this kind of construction applies to it. It's like a Z. It's a superset of U. So if I take the graph that corresponds to it, I can infer, hopefully, some of the entries of U, and it turns out that you can prove with high probability that you can infer, in fact, the first log k entries of U. That's a fact, okay? And then once you have these T entries, you can, again, construct these different WPs by adding the U0Ps to them and intersecting them all. That gives you UT. And then, lo and behold, the support is just the union. Laser pointer would have been easier. It's just the union of the first, if you will, T entries of the support that we found from the graph G and the set UT that we found from intersecting these W's. So this is this is a quadratic time algorithm. I mean, the most complex thing is computing this G, which, because you have to do all pairwise distances, is quadratic. Everything else is trivial. And this works. And so it doesn't work always, because if it always worked, we would have solved the turnpike problem in its full generality. The theorem says that the algorithm works if the sparsity is a little less than root n. So with high probability, all the steps in the algorithm make sense, and the thing works. Okay? There's no guarantee beyond that. So we haven't really solved the turnpike problem in its full generality, but we have when the sparsity is root n of the entire support of the signal. Okay? And I won't go through the proof. So there's the random graph stuff that goes into it. I will say this, though. When we started this, we had no hope of doing better than root n. In fact, there's no way you can do better than root n. And can anyone see why? So if I have a signal whose support is root n, I just randomly, choose root n entries to be non-zero. And then if I convolve the signal with its mirror image, what will the support of the signal be, of the autocorrelation? So if I have a signal that has sparsity k, and you convolve it, you're going to get an autocorrelation that, with high probability will have sparsity k squared. And so once you hit this root n sparsity, if you're above that, then the support of the autocorrelation is full. And so there is no information from the support of the autocorrelation that you can get. So in some sense, we couldn't expect to do better than root n. And this algorithm in quadratic time does that. And so these are simulations for n equal to 512 and 10,024. And if you note, in my previous example, I had n 64 and 128 because we were solving an STP. And as Mariam will tell you, that takes a while. But this, we can easily do 10,000, whatever. It goes like that. But anyway, I only did 1,000. But you can see for 512, the square root of 512 is, what is the square? 22, 3, something like that. And so you can kind of see the threshold is around 20. For 1024, the square root, I should know, is 32, and this kind of looks like that. So the simulations kind of jive with the theory. I don't know if I should do an example. Are we short on time?
Just a couple of minutes.
Do you want to see an example? anyway, if you just to see how quick this is. So this is an example. It's a little bigger than the one I did with the backtracking method. I mean, if you try backtracking on this, it'll take you a while. But here it's very easy. So you look at this W, and then the first thing you do, so U0 is 0, U01 is 3, right? Because the second largest guy is 179, right? So one end is at 182, one end is 0, and so the next one is at 3 because 179 is the second biggest, okay? And so the recipe basically says that construct W1, which is W plus U01, and that we can do because U01 was 3. And when you intersect it with W, you get this. And then the next step says to construct the graph with this. And it turns out this graph only has 2 edges. And so from those 2 edges, we actually infer, well, it's actually 1 edge because, yeah, it's 5 and 17. You infer these 2 points, 5 and 17. So that's kind of like log of the sparsity. It's 2. And then you compute W2 and W3, and you intersect them, and you get this. And lo and behold, you put everything together, you do get the support back. So it works. It's incredibly fast. So I'll skip the signal recovery part. So once you have the support, then we just run the, I guess this is what where's the program? We essentially do this minimization because we have the support now. And as I showed you, this minimization works if you know the support up to n over 2. So with root n, it certainly works. And so there's proofs and all, which I will skip. And let me kind of wind down. Again, so this was just kind of, in some sense, a curiosity that we did. So the phase recovery problem, as I said, it's classical. It's a classical problem in signal processing. It has numerous applications. And as I said, because there's ambiguity about the phase, you need some form of a priori information. You need to know something about the signal structure. You need to know something, okay? And so as I said, recently, I'd say the last 7, 8, 10 years, sparsity has gained significant traction as a paradigm in, for large data sets and so on. It's called compressed sensing. And so we looked at the use of sparsity in phase recovery, and it wasn't just an idle curiosity. There are many applications where it's a very natural thing to look at. Okay? So what were the results? We showed in principle, as long as the support is not periodic, even if you have a few 0 entries in the support, that's enough to recover the phase. That was good news. Okay? Then we showed that the standard lifting method does not work. As I said, that's because you had these multiple solutions, and the ambiguity kind of screwed things up. And so what we did was develop a 2-phase method that works for sparsity up to root n. We found the support of the signal from the support of the autocorrelation. Once you have the support of the signal, then you can do the lifting technique. And again, there's no hope in this sense to go beyond root n because the support of the autocorrelation function can never give you more information than root n. It becomes full after that. Okay, and so the method we had to find the support was actually combinatorial and very, very efficient. So there's a lot of future work. So this was all noiseless, everything I described. Once you have noise, things become more complicated. And there's things you can do. I won't talk too much about that. The more interesting thing is the second bullet, right? There's a huge gap between what can be done in principle, which it looked like, as long as you have even a few 0 entries, that's enough. So you should be able to recover sparsity up to order n. But what the algorithm guarantees is at most root n. So that's a big difference, especially when n is big. And so it's not clear if this is a fundamental barrier. It might be that efficient algorithms cannot go beyond root n. Or it might be that we're just not clever enough, and there might be ways to do that. So I'll stop here, and if there are any questions, I'd be happy to take them.
So any questions? Yes.
You said that with the
actually, so that's an interesting point. So you can have some of the distances be repeated. It's okay. No, you don't need to know. In the original turnpike problem, you know the multiplicity. And the reason is because it comes from the bioinformatic thing and because you kind of get all the pairwise distances. If one is multiple, you'll measure twice, the mass in some sense. But we don't need that. Certainly the algorithm we have doesn't. The original problem assumed the multiplicity.
Actually, I have a question also. So in the original SDP problem, the issue was basically symmetry.
Yes.
And if you can break that symmetry, then if you find one of the solutions in the optimal set that's on the boundary, for example, will be done. Are there other ways to do that? For example, perturbing the problem or
Yeah, so that's what we've been doing. So what we're doing now is the following. I can give it away. Though Kishore would not like me to give it away, but I will. So what we do right now is we optimize not an L1 norm, but a weighted L1 norm. So we kind of choose some random weights. And so we're hoping that this will bias us towards one of the corners of this convex element. So it doesn't take you all the way to the corner, but it biases you somewhat. And so what we do is you look at the solution, and when you do a random W, the solution is not rank 1, but typically it has a dominant eigenvalue. It's close to rank 1. Whereas if you do it without the weighting, you just get a full rank blob. And so if you, what we've seen is if you look at the largest eigenvector, it has information about the support. And so we're kind of iterating about that. So we use that to guess something about the support, then redo the weights. And that seems to work well. So we can do it for small examples. So for example, for 64, n equal to 64, whereas this method works up to 8 or 9. That one works up to 20. So we can get up to sparsity 20. But that's just empirical evidence. We have no proofs or anything like that. But the point exactly is that you need somehow to break the symmetry of the problem. Because usually the reason why these convex relaxations work on non-convex problems is typically the non-convex problems, even though they have lots of local minima, they have a single global minima. And so a good relaxation under some conditions can capture that. When you have multiple global minima, which you have here, then the obvious one will not. You need some kind of relaxation that somehow breaks that symmetry.
Thanks. Any other questions? More?
Can this algorithm being applied to any complex signals?
Yeah, I think so. Certainly, because we were just looking at, so everything I said about the support of the autocorrelation being related to the support of the signal remains true. Because in some sense, in this algorithm, the reason why this only takes us to root n and has no hope of doing that is we're ignoring in the first phase of the algorithm to find the support, we're ignoring the value of the autocorrelation entirely. We're just looking at its support, and what that support is doesn't care whether the signal is complex or real or whatever.
Okay, if there aren't any more questions, let's just thank Babak again. We really appreciate him taking the time to come here, given the busy schedule. Thank you.